All right, hello, welcome. It's great to have so many people on the call today on our webinar. My name is Kathy Hoverman, and I'll be moderating today's webinar. This is put on through the Joint Committee from American Society of Civil Engineers, Environmental and Water Resources Institute, and AFSS Bioengineering section. It's called the Joint Committee on Fisheries Engineering and Science. The webinar is being recorded, and you should be able to get to that in a few weeks. What we've been doing is posting it on LinkedIn when it's available. And I see a couple folks requesting to record, and it's already being recorded, so please stop requesting that it be recorded. And I appreciate that. So anyways, this will be available on our YouTube site when we get it processed and placed up there. We do have, as I mentioned, a LinkedIn page, as well as a few other resources on our committee's website. Both of those things can be found through this link and this link that's on here, both an email address and a QR code, so you can get to those things quickly. Part of our committee is providing the steering committee that then selects a conference location. So our next conference is being held at UC Davis. It is May 4th through the 8th at the University of California, Davis, which is strategically placed between Sacramento and San Francisco. The theme of the conference is Headwaters to Sidewaters to Estuaries, Improving Watershed Connectivity and Processes through Restoration, Revitalization, Remediation, and Reintroduction. The organizing committee is still working out the details for the conference, but it looks to be pretty amazing. There are going to be several workshops and tours of the local area. May is a great time to visit the Central Valley of California, and the weather's typically sunny and warm, which those coming out of the north, more northern states might appreciate that in early May. Plenty to see and do in California, so we hope that you'll consider joining us at that conference. As part of the conference, we also solicit nominations for 2 awards: the Career Achievement Award and the Distinguished Project Award. So both of those calls for nominations are open now. Nominations end January 16th. So go ahead and start getting your head around a project that you might think is a good candidate. All the information, the criteria for nominating is all through this website. So go ahead and take a look, see if there's a colleague or somebody that you respect, that you really want to put up for the award, or a project that's just done great things to open up fish passage. Our next webinar after this one will be December 3rd. It'll be on the White River and Mud Mountain Dam in Washington State, which is roughly 35 miles southeast of Seattle and just downstream of Mount Rainier National Park. This is a uniquely challenging setting where flood control operations, ESA-listed species, and tribal fisheries all intersect. So we're looking forward to that next webinar. And then we also are in the process of selecting a date for a recently published technical report from Forest Service on culvert resiliency. So look for those announcements coming out in the coming weeks for the December 3rd one, and then towards the end of the year for the following one. As always, just a quick shout out to my colleagues, my friends who are on this task committee with me. Really appreciate the work that Andy, Mike, and Abul do to help keep this task force going so that we can continue to find speakers and bring these out to you. So speaking of that, I want to introduce our speakers for today. We have 3 speakers all speaking together over their work together. Ben Mader is a senior hydraulic engineer with Verdantis Flow Labs, formerly known as Alden, based in their Fort Collins, Colorado office. He specializes in the use of 2- and 3-dimensional numerical modeling to solve problems at the nexus of engineered and natural systems. Problems of particular interest include those related to water treatment, spillways, river mechanics, sediment transport, and fish passage. Greg Allen a principal and senior consultant, also at Verdantis Flow Labs, based out at the Alden campus, with over 25 years of experience in hydraulic and fish passage engineering. He specializes in fish screening, fish and eel passage design, and turbine survival modeling for hydropower projects, dams, and large water intakes. And then finally, we also have Mike Burke. It's a principal water resources engineer who leads Interflu's Maine office. For nearly 30 years, Mike has focused on restoration and connectivity in rivers, floodplains, and estuaries across North America. Mike has been engaged at all three phases of assessment, planning, and design and implementation, and recently celebrated 20 years at Interflu. So with that, I'm gonna go off screen and turn over the sharing to Ben and Greg and Mike. Take it away, guys. You all are very muted. Let me see if I can help you with that. All right. Ben, see if you can unmute now.
Can you hear me?
Yep, sounds good.
Awesome. Great. Thanks, Kathy. Thanks for that introduction. Yeah, Greg and Mike and I are excited to present to you guys kind of a high-level overview and status update on three very different but very interdependent fish passage projects that are either recently completed or ongoing on the lower St. Croix River, which the lower St. Croix forms the border between Maine and Canada, New Brunswick. And these are three dams in series on the lower St. Croix that are currently impeding fish passage to the upper watershed. This photograph you're seeing here is the upstream-most dam, the Grand Falls Dam. And looking beyond that, you see the vast forested watershed, which has a lot of excellent spawning habitat for river herring. So, like I said, the river, the St. Croix River, or the Skutik River, as it's known to the native Passamaquoddy people, forms the border between Maine and New Brunswick. You can see the river there in black. Let's see, I'm going to get my laser pointer. The river forming the border there, you can see its watershed in green. And you'll notice there's lots of lakes, glacial lakes in this watershed that have, many of which have been accentuated by the construction of dams. And those, like I said, those lakes provide excellent spawning habitat, making this watershed pretty unique in the state of Maine for just the production potential for river herring. But it's not just river herring. Historically, this river has seen very large runs of Atlantic salmon. We have American eel and American shad as well. Not only is it ecologically important, but also it's culturally important to the Passamaquoddy people. And I like this image here because it shows the traditional homeland of the Passamaquoddy people. And you can see that the watershed sits squarely in the middle of that traditional homeland. So these runs really existed, very large runs of sea run fish up into the 1800s. And I like this quote back from the 1880s that sums it up nicely, talking about the uniqueness of the St. Croix. The St. Croix is remarkable, even among the rivers of Maine, for the great extent of the lake surface among its tributaries. These lakes afford breeding ground for great numbers of alewives, river herring, and in the Main River and its branches, here the salmon and there the shad found their favorite haunts. And those large runs really kind of came to an abrupt end. All but stopped back in the early to mid 1800s with the construction of dams on the lower reach of this river. So presently, there's three main hurdles shown in this map of the watershed. highlighted. We have the downstreammost one, which is the Milltown Dam, shown in this lower right image here that was recently removed. Mike will be talking about that one. The next one up is a hydroelectric dam owned by Woodland Pulp. That's the Woodland Dam that Greg will be talking about. And then I'll be wrapping things up with a discussion of ongoing work, design work at the Grand Falls Dam, which is shown in this upper right image. And one thing I want to point out here, I talked about the interrelatedness of these dams. It's really because 98% of that spawning habitat that we talked about for the river herring lies upstream of the Grand Falls Dam. Okay, with that, I'll turn it over to Mike to talk about Milltown.
All right, thanks, Ben. Thanks everybody for having us along today to talk about these great projects, all very unique amongst themselves. And I think we could all spend probably a few hours talking about each one of these projects. So this is going to be a rapid cruise through these projects, but I think will be also informative and give folks a good orientation to the same efforts on the St. Croix. I wanted to just do some initial acknowledgments in addition to Ben and Greg and the Joint Committee for having us along, but in particular acknowledging New Brunswick Power, the Pescamacati Recognition Group, Division of Fisheries and Oceans, and then our teaming partner GHD Limited out of Fredericton, as well as other really important players in this project, including Dylan Consulting and Kleinschmidt, who handled the permitting on both sides of the border, and then Pennacon and Sargent are the constructors who did all the heavy lifting to carry this project across the finish line. So you see, again, a familiar graphic. Let's see, click, there we go. Familiar graphic over here, but you see the Milltown is the first main stem barrier above Passamaquoddy Bay. You're getting into the lower St. Croix with a really tremendous tidal range there in the 20 to 25 foot range. And then we'll focus on the Milltown site in particular, and we'll just start by looking at about as early of a graphical representation as we've found. This actually happens to be hanging in the basement of the library in Calais, Maine, but really this is a, I think, 1874 depiction. And at that point in time, and you'll see some imagery here coming up, really the upper portion or the upper Cascades that had been heavily developed by that time. The lower falls, which was referred to as Salmon Falls, actually fairly lightly developed at this stage. And we'll talk about that a little bit. But I think a key thing from this graphic I want to point out is just, you talk about Salmon Falls, but in contrast to a very crisp and discrete fall, instead it's a dispersed exposure of bedrock chutes and drops and things like that over some distance of the river. And that's important in thinking about solutions at this site. So in terms of, Ben made mention to the Pescamacati, Pescoto-Macati or the Passamaquoddy people. And this was squarely their land historically for 13,000 years or more, all throughout the watershed. And so they're the primary driver of all these efforts. And in particular, one of the most important locations was here at the Salmon Falls. Somewhat tragically, in 1786, at least archival records indicate that there was a reserve built here of about 200 acres in what would today be Milltown. Tragically, however, just a few years later, in 1802, most of this reserve land was granted to the Anglican Church, and the remainder being given over to private entities. So a really kind of tragic development, but hopefully a story at the end of hope for the future. Let's see here. Get confused here in the vortex between our screens for this presentation. Let's see how this works. Okay, here we go. So moving forward in time, early development of various water control structures here in the late 1700s and into the early 1800s. Really the first one that obscured a significant portion of the river channel was in 1825 and included no organized fishway. And in the black and white photo here, you see late 1800s, early 1900s image with the Canadian Cotton's mill over there at the right, and this follows shortly after the first generating station was constructed here in 1881. And as you'll see, ongoing major upgrades occurred over the next century. But really the first major dam and power upgrade following the initiation of the generating station was in the 1920s, when additional powerhouses were constructed across the river and additional spillways over here on the United States side of the river. New Brunswick Power took ownership of the site in 1958 with a modern quote-unquote fishway added in 1960, upgraded in the 80s and multiple times also since that time on through the 2010s. So we'll just fast forward with some quick snips to see, what the site looked like up until a few years ago. As I was mentioning, well, in this image, the cotton mill is no longer here on the Canadian side of the river, but the original powerhouse is still here. And then 2 additional powerhouses were added, like I mentioned, in the 1920s, as well as a concrete stop log spillway, a rollover spillway, and a gatehouse, all proceeded, succeeded those 1920s upgrades. And so this was, as the site looked from downstream as of 2022, and operating head was about 8 meters at the site. So we fast forward to then the removal process stretched out over the years of 2023 and 2024 after focused planning and permitting from 2019 on through early 2023. And these are just a little bit of foreshadowing of additional things we'll see then moving forward through the presentation. And lastly, just a video or a graphical snip here of then what we look like today, or very similar to what we look like today from that same vantage point, looking up at the formerly dammed location. So what made this project happen? What were the motivations and the opportunities and the decision factors that really made it come to fruition? First of all, the motivation was a longstanding interest in removal of this site by First Nations and Passamaquoddy people, as well as many dedicated other collaborators on both sides of the border for really looking towards the ecological restoration of the river. But then in conjunction with that, in coincidence or event or developments that came along that further enabled the feasibility was that New Brunswick Power was entering into final arrangements for their new Fisheries Act authorization, and discussions around offsite mitigation credits had been identified. And then the last trigger point, if you will, was in conjunction with that, this site in its present condition in 2022 generated about 2.7 megawatts of power and was in significant need of significant upgrades and modernization. And the final trigger point was that the cost analysis came down that it was going to be a much less expensive project to remove the dam and use it as mitigation for the Fisheries Act authorization than it was going to be to modernize and bring the facility to a more productive and economically viable state. So we got a little bit of a triptych of imagery that moves across the bottom of the screen here. Looking up at the site in its operating condition as of 2020 or so, And then really this is the early vision of what was thought could be a, the resulting condition of the river after removal. And so in the center one, you'll see the ghosting of the facility, and then a fully unobstructed river here. So just to add some site context, as we mentioned, the former facility is here in the center of the screen. In this particular imagery is actually during a facility drawdown. And so you see the impoundment area, which extended up to the base of another Cascades, was drawn down, and some marginal surfaces are exposed. The site is just above the head of tide, highest astronomical tide, presently maps out about the location of this line, and a fairly steep channel downstream until things start to bottom out closer to the town of St. Stephen. Just some additional features. So we've got the Milltown neighborhood of St. Stephen here on river left, town of Calais, Maine on river right, and we've got a former, well, actually once a day, twice a day used rail trestle right upstream of the dam. The former Canadian cotton site here on river left, just upstream of the dam. And one of the significant features also that I'll point out is that the international boundary snakes, I'm just showing a segment here, but snakes right through the facility and right through the project site. And you would guess, of course, conveniently actually sliced right through, not physically, but virtually one of the operating units in the dam. So as you can appreciate, that added some complexities to the overall implementation of the project. So just wanted to highlight some of the key findings of the assessment when the dam removal project got going in earnest. And I've got just a couple of place markers here that I'll highlight. One is that our evaluation of the presence of accumulated sediment yielded almost no sediment at all. There was really a couple of small pockets of sediment and margins, one of which you can see in the background here. But by and large, this operated facility had regular drawdowns through time, and with upstream, the nature of the watershed upstream, marginally low sediment loads to start. So that was one potential issue that was off the table after the assessment. A second piece of that then, well, I did just refer to the complexity with the border running right through one of the powerhouses. And generally the powerhouses were in Canada and the spillways are in the United States. But, complexities about, staging field work we could get in the water in Canada as long as we did not touch the shoreline in the United States, even though, we were maybe on one side or the other of that virtual border. Some other findings we came to realize once the facility was out, the entirety of the river flow would be concentrated through this bedrock narrow and no longer flow over the top of this ledge, except in very high, very cataclysmic flows. And then a couple of other items. We did find a lot of evidence of given the long history of development of the site, a lot of presence of legacy and relic structures that during the time of the assessment, with the ability to access those areas, were hard to discern whether they were actually legacy structures. Some were clearly obvious, but the contact point between legacy structures and bedrock features was very hard to cipher, and that led to some of the uncertainty going into construction that I'll talk about a little bit more in a minute. And lastly, we did find evidence that there had been modification of the historical and historic falls, and so there were certainly some uncertainties about that. And ultimately, we looked at several scenarios, whether we could just remove the obstructions to flow and be reasonably confident that safe, timely, and effective passage would be there, or whether there was some proactive measures that needed to be planned for. And we'll talk more about that. So some of the key design elements, the real guiding, the two guideposts of this project. I think I just lost one of them, or maybe it fell off the screen. There we go. The first was to remove all human-made impediments to flow. And then the second was to provide sustainable and resilient, safe, timely, and effective fish passage in perpetuity for the utilizing native fish, sea-run fish community. And so that last one actually did have quite a bit of influence on the ultimate design solution, because this was a key mitigation piece for NB Power and DFO. There really did have to be some pretty significant assurances of safe, timely, and effective, essentially on day one. So taking those guideposts forward, I'll then highlight some of the design elements that responded to that. And this is essentially right after the completion of construction during demobilization photo here. And so I've ghosted in the general alignment of the powerhouses, the spillways, and the gatehouse here. And I'll just highlight a few things. To get at, I guess I'll just get right into thinking about the day one necessity to provide safe, timely, and effective. It was ultimately concluded that there was too much risk in not being able to ensure passage on day one of performance, that there was some proactive bed enhancement done in the tail race area, so the area downstream of the white line, and really going over to the U.S. shoreline in the zone that I'm circling with the pointer here. This was the area where it was anticipated that there could be a substantial a multi-meter vertical discontinuity, and that was just too much risk to wait until the end of construction for. So proactively planned bed enhancement in the form of essentially a bank-to-bank nature-like fishway. Other design elements I referred to, dealing with a tremendous number of legacy structures, even up until a few days before the final climax of construction, still pulling out timber structures from the river up in here, and seeing how passage conditions responded in the near head pound area. Some selective shaping of bedrock in that area as well. And then this former Canadian cotton mill site was a controlled site, had, as you can imagine, industrial legacy soils, and in addition, previously were retained by a vertical retaining wall that was 10 feet above the water and was going to turn into about 25 feet above the riverbed. And so that cribbing was removed, and the bank sloped with heavy toe protection, and then a bank restoration component above that, and overall overbank restoration that will eventually be turned over from NB Power to others. So some of the novel implementation challenges of this site, and just a quick orientation to the imagery here. I pointed out the upper cascades above the impoundment, and I'll just trace out about the head of the impoundment here with the laser pointer. This is about as far as the backwater extended up. And so this is the next section of passage upstream of the Milltown site. So some of the challenges that were navigated successfully, including the fact that the international boundary, not only split the site, but split a generating unit. And we actually somehow, although it was never written thus, somehow were able to temporarily virtually move the international boundary to a more logical separation of work between work in Canada and the United States. So that was an extraordinary win that really enabled the project to proceed. Other things, as you can imagine, going through permitting in not one but two countries, thinking about sequencing construction and licensing and things like that in two countries. And then really some of what I referred to before, thinking about what can be reconstructed of the underlying bedrock, and thinking about the stakes for passage and what can be known, what is really unknowable until you open the site up, and putting measures in place to be able to both have enough assurance, but then also be able to capitalize on the opportunities that do emerge through that discovery process to really optimize the finished project. And then lastly, I made reference to the controlled site, but lastly, a design issue, especially with the nature-like piece, is that both advantageously the fish passage is the river and the river is the fish passage, but in terms of that's a lot of water, it's a big river, and so certainly a lot of nuance to, even though it is such a large river, a lot of nuance to the hydrology, hydraulics, and especially water control and sequencing during construction. So lastly, I'll just wrap it up here with a couple of final outcomes and feedback observed since the construction of the project. So first of all, project was implemented safely and successfully. It has been passing a lot of fish thus far. The Woodland counts can no longer be done at Milltown site, so the count is now done up at the next upstream site, and that has increased about 2.5-fold in the first year, which was really the project was only half constructed at that point. So the future looks bright. There is a multi-year effectiveness monitoring program being led by PRGI, or the Passamaquoddy Recognition Group, and Canadian Rivers Institute, which is in support of NB Power's adaptive management program. And due to the historical nature of it not being a smooth site to pass anyway, and being pretty opportunistic passage historically, the target was set at a 65% passage per 24-hour target in year 0.5. So between the first construction seasons, the result was about 78% effectiveness within that 24-hour window, and data from this past year is being crunched at the present time. To me, I will just say this was an extraordinarily rewarding example of the cooperation across the border, signified by this old postcard I found in an antique shop a couple of years ago. I guess this is actually kind of an annual event there between Calais and St. Stephen. So that was great. And then I'll just comment my observation on just the extraordinary significance of this site to the First Nations and Passamaquoddy people, and just sharing, the potential for the full circle to come back around about having that land set aside and then taken away. And I think potentially the long-term trajectory is this land goes back to the Passamaquoddy. And I'll just say this photo at lower right was during an event last June that was held to welcome the fish home. And half of those observers in that image are just watching clouds of river herring ascend up through the river, and the other half are observing a water ceremony that's just off the screen there. And I can just summarize it. It was a very joyful, extraordinarily joyful feeling to be there and experience what the significance of that project to those people. So with that, thanks for your time. And I guess we'll pass it over to Greg.
Thanks, Mike. I forgot to mention at the top, but in terms of just numbers of production, talked about great production potential. Estimates based on habitat size, acreage are 20 to close to 80 million adult fish in an annual run. So if true, if realized, that would be one of the largest, not the largest run in North America. They could realize that. All right, great.
All right, I think I have control. Just trying to advance the screen. Oh, did it go? All right. All right. Yeah. Thanks, Mike. Yeah. So as the fish move upstream, Milltown is now removed for the past 2 years. They hit the Woodland Dam, and so this is the next dam upstream. You can see in the upper right, it was built in roughly 1905. That's a colorized historic photo there. You can see log sloughs right just off to the right, and the powerhouse to the left, and the tail race, and then the dam in the upper right. And the image in the lower left is what it looks like today. So it's an operating mill. There's a hydropower plant there. I can advance to the next slide, I think. Right. Yeah, so this is what the project looks like. And so the Canadian border there is goes right down the spillway channel. You can see the dam. There's a working hydropower intake. There's a mill water intake. There's an existing ladder that wraps around what we call this area here an island. The only way to get access to it is through the powerhouse here. It wraps around the island, a couple switchbacks up to the head pond. There's an elevated electrical duct. This is a feed to the entire paper mill. And so that's something that we need to be aware of. And there's also some overhead wires that cross the channel. You can see them there. And they cross from the Canadian side and then move on to the US side. So that existing fishway that was built in the 1960s, it's a denial ladder. It's roughly 49 feet ahead, and it's over 700 feet long. It's reached the end of its useful life, really. It's in poor shape. It did pass over 1 million fish back in 1986. And with the last 2 years with Milltown out, the counts have been up around 600,000. So that's really promising, and that's impressive for a denial ladder. Although the effectiveness studies show that it's about 30% efficient in terms of getting herring upstream from the tailwater here up to the head pond. The amount of habitat upstream, as Ben had mentioned, it's in excess of 26 million. That's Maine DMR's estimate of the potential run size. I know DFO's estimate is greater than like 60 million. So there's a lot of potential here at this site in terms of potential run size for alewives. There's a downstream passage here as well. It's went too far there. Sorry. Downstream passage. So there's a bypass in the middle of the existing intake racks for the hydropower station, and that transitions to a 24-inch diameter pipe that discharges to the tail race. The approach velocities to the intake are really low. They're at 0.7 feet per second. So that's good news when we look at, say, new designs to improve fish passage at this site. And so the site constraints, it's an operating mill. There's no vehicle access to this island area. And there's some critical infrastructure that as we design new fishways, we need to avoid. So there's this mill water intake that's critical to the paper mill's operation. There's this elevated electrical duct that's also critical. That's the main feed to the paper mill as well. And then there's the overhead wires that cross the site. So those are present some challenges as we look at options for fishway designs. And so some of the design tools that we used going into this in terms of surveying, we had some LiDAR surveys done. This is an image showing that LiDAR survey. because it's really important to know where everything is in kind of 3 dimensions as we lay out our new designs. We used 3D models and computational fluid dynamic hydraulic modeling as well extensively as we move forward with designs. Okay, so in terms of what's proposed, so here in the lower right, you can see we have an access bridge. And so that's important for long-term maintenance of the fishways as well as construction access. What we've designed is a fish lift. And so that fish lift has an entrance in the general location of the existing Neoladder entrance. And so as fish move upstream, they would enter the, let's try that again. They would enter the fishway channel. They would be trapped over the hopper. The hopper would pick them up, and then they would be discharged into an exit flume and swim out to the head pond. In addition to that, we had designed a fish ladder. This is a pool and shoot fishway with an entrance adjacent to the spillway channel. And so that runs upstream with some switchbacks and meets up with the exit channel to the fish lift. Then for downstream passage, so we're replacing the existing trash racks on the hydro intakes with 3/4-inch clear space trash racks. That would exclude eels, herring, and other fish from the intake. And then we have some bypasses. There's 2 bypasses there. They go through the dam into a flume, and then that transitions to a pipe and then discharges adjacent to the fish ladder. In addition to that, the fish lift exit flume also acts as downstream passage route. And so fish would travel down that flume, and at the end there's a weir, and that transitions to a pipe and then discharges adjacent to the fish lift entrance. And so these are some images of some of the models together as part of the design process. You can see the fish lift there on the left. This was a 3D Revit model that really helped us pull together the CAD drawings as well as the structural analysis. And it's also provides a good visual of what the fish lift looks like. You can see the steel superstructure that supports the hoist that lifts the hopper up to discharge the fish into the exit channel. And to the right there is an image of the elevated portions of the pool and shoot fish ladder. And so that was important as we tried to avoid all the various infrastructure on this site. So this is another image, and you can see on the left here some of the challenges we had with avoiding existing mill infrastructure. This up to the left here is our downstream passage channel that transitions to a pipe, and that channel sits on the back side of the dam, which is also on top of the powerhouse roof. It's above the roof, and so we have to avoid the roof. Then we have to dive and get below our proposed fish ladder here. We had to miss the supports. We had to make sure that the pipe has enough clearance to miss the overhead wires. And in addition to all that, we had to make sure that the hydraulic conditions within the pipe are good. That we have enough water depth, low enough velocity, that we don't have any hydraulic jumps within the pipe. And this image just kind of shows that flume as it transitions to a pipe. You can see this is overlaid on the point cloud from the LiDAR data, and some of the design processes as we went through this. And we used hydraulic modeling pretty extensively for nearly all the components for the fishways. The lower left is some of the tail race modeling that we did of the existing conditions so we can understand the velocity. The upper right, we had a model of the fish lift entrance flume. We wanted to make sure that we had good uniform velocities over the hopper channel and all the way out to the entrance. In the middle image there is a model of the pool and shoot fish ladder. And that bottom image is a model of the hydraulic conditions within that bypass pipe that we were just looking at. And there were a lot of folks involved in this, a lot of collaboration. This project was led by Maine DMR, Department of Marine Resources. We had really good cooperation with the owner, as well as all the other stakeholders. NOAA provided quite a bit of funding for this project, but there were other grants involved as well. And in terms of the design team, we had On Point Construction Services help out with constructability and estimates. ECI provided electrical and controls design, and Kleinschmidt provided the intake rack, and there's a new rake design as well. And the rest of them are listed there. All right, so I'll hand it over to you, Ben, and you can present the next project.
Thanks, Greg. Yeah, so this will be a sneak peek of what's going on at Grand Falls currently. We're a little past 30% design up there, and we're running a little bit short on our presentation time, so this will be kind of a high-level overview of what's going on. So much different site. I mean, drastically different than Woodland in terms of just the existing infrastructure. So this site is a hydroelectric dam. It's on the main stem of the St. Croix right here. Provides supplementary power to the Woodland mill that Greg was just discussing. It was built back in 1913, 1914, created the Grand Falls flowage here. And during the construction of the dam, they excavated with a steam shovel, shown in the upper right image, this power canal that leads down to the powerhouse, which is shown in this image here. You can see it's mostly forested, very, very rural, a little more real estate to work with in terms of fishways. Hence, the design here is going to be a nature-like fishway. So the nature-like fishway, just some design aspects. The right image, we could see the powerhouse here, the power canal, the nature-like fishway alignment has an entrance down here where the draft tubes exit into the tail race. We have a gated control structure there to get the attraction water jet that we want. And then it transitions to the nature-like channel that winds its way up all the way to the power canal here, where there's a flow control gate to deal with the fluctuations in that head pond level. So it's about 50 feet ahead here. We're targeting a riffle slope of about 1.5%, which is kind of based on another project we did on the Croix River in Maine, Sacarapa Falls, which was a dam removal and kind of a channel modification project that shown in this image here had about a 1.5% slope, and 2 consecutive telemetry studies have shown greater than 95% passage of river herring there. Given that slope and that head, we're currently sitting at a pretty long nature-like fishway, 3,700 feet, which would be one of the longest in the world. Channel bottom width of 30 feet, roughly 8 resting pools, and a capacity of 160 to 320 CFS, which is at 5 to 10% of the station capacity. Okay, so here's a rendering of what that would look like. So to orient you, here's the powerhouse. Here is the St. Croix River. There is our entrance channel, which transitions into that nature-like fishway. Now, this is an interesting site because it looks forested, it looks nice. But there has been lots of legacy impacts here. Obviously, logging. Another big impact was with this excavated power canal. In the image I showed, they put that material on rail cars, ran it down this hillside, and side dumped it over here. We were pulling out cut lumber down 13, 14 feet deep on this hillside. So the nature-like fishway, we would kind of square up and cut right into that hillside. So there's a big geotechnical component to this project as well. This cut here would be about a 30-foot deep cut. So quite a bit of excavation and earthwork. By the time we get up to up in here, the invert of the channel is about at grade, so we'd be constructing the banks as essentially levees before diving back into some more legacy fill up here. Here on the right is just another view of that. All right, so you might have been asking, what are all those little gray structures in there? So those are our roughness elements, if you will. And we think about nature like fishways, we often think of either kind of a pool drop type morphology, or maybe a rough and rock ramp or boulder garden or something like that. And I was trying to think about, is there a way that we can maximize depth and volume as you would with like a pool weir type morphology, but then eliminate the potential velocity barrier that you get with that weir. So you could, at the other end of the spectrum, you could do a rock ramp where you no longer have discrete velocity barriers at weirs, but you might have shallow and pretty fast flow. So the concept that I kind of developed, shown here in this sketch, so flow would be moving from left and right in this particular image. And we'd have essentially a series of these angled alternating veins where you have a rock vein that ties in on this bank at a high elevation. So we're looking down on the channel, and then it points upstream and dips down. So you have a low point on the vein where the flow comes across. And then it splits around a boulder cluster. You have a high velocity channel going this way and kind of a sneak route for the fish on this side. And you even maybe turn the flow back on itself to provide some extra resistance on that sneak channel. And then you just flip it on the next vein down. And this was kind of inspired by two things. One is a Tesla valve, which I don't know how many people on the call have heard of a Tesla valve, but it's essentially a check valve with no moving parts, often used in a very small scale tube kind of applications where you take the flow, you split it, you turn it one lobe back on itself to provide resistance. So we want to provide resistance to slow that velocity and increase depth in our application. But this is an open channel. So the other inspiration is, a common aspect of stream restoration is bank protection using log veins. So this is a log vein shown on the right. The root wad is tied in at a relatively high elevation, points upstream, and then dips downstream. And so as the flow comes up, more and more of this vein is engaged, and you have the deep part over here, but then you're creating a nice stagnation region near the bank, slowing flow, and then you no longer have a constant crest weir, but it's essentially a sloping crest weir. So you're maintaining depth and relatively, good depth and flow conditions for the fish off the tip of the vein. So this is kind of a mock-up of what that would look like. You can see that kind of my sketch rendered here on the left side, and a hypothetical track for the fish going up those sneak routes. So we did, like Greg said, a lot of CFD modeling at Woodland, but also here. So we're showing velocity on the left with a rendering of what those veins would look like without all the fancy texturing. We have a little human shown here holding the last Atlantic salmon caught in the St. Croix. And we can see that the flow, it does kind of, it comes over the vein. We have a nice deep region here with relatively low velocities, and we're essentially bleeding off that high velocity down one path while providing a lower velocity path for the fish over here. This is an image showing depth on the right. And as we come up from 160 to 320 CFS, they flip back and forth, the hydraulics stay pretty similar as just more and more of that vein gets engaged. So comparing that to, say, a boulder garden type approach, we've got the vein concept on the left and more of maybe a traditional boulder garden approach on the right. So we have nice streaming flow with the vein concept. The boulder garden approach on the right doesn't look too bad, looks pretty good. You do have a little bit shallower depths, so that is a concern. But what's interesting is you get higher and higher flows, you start to get maybe some velocity barriers that form between boulders in certain places. It might be somewhat unpredictable, and the depth doesn't come up that much, whereas you're maintaining the depths in the vein concept. So an interesting kind of novel concept that we that we think has a lot of promise. The CFD modeling has been really great to optimize that and to build confidence in that and share kind of this relatively complex concept with the other stakeholders. So similar players in the collaboration at Grand Falls as down at Woodland. The Nature Conservancy is leading the design effort currently. We Verdantis are leading the engineering design, and a lot of input from a lot of players. So in summary here, we've talked about these three very different but very interrelated projects. As I mentioned, 98% of that spawning habitat is upstream of the third project, Grand Falls. So they're really tied together, but very different. And all these projects have ecological benefits, social and cultural benefits, as well as the economic benefits that we've discussed throughout this presentation. So with that, the key takeaways, Milltown, Woodland, and Grand Falls are the three main barriers. We've checked off Milltown. It was a great success. Woodland, we have some pretty novel and state-of-the-art fishway designs, very technical. They're currently out to bid with targeted construction in 2028. And then Grand Falls is a very long fishway with, I think we were at roughly 130,000 cubic yards of excavation up there with a novel morphology. There's also downstream bypasses underway at Grand Falls as well. And that would be the last hurdle to unlocking all that great spawning habitat further up in the watershed. So I think that concludes our presentation. Sorry, we were very ambitious with presenting all this to you, but excited to do so.
Yeah, thanks, guys. This is very cool stuff, indeed. Unfortunately, we have 3 minutes left, so we've got 3 questions loaded up. That's probably the very most we're going to be able to get through. So I'm just going to start off with the first one, and this came in, I believe, when Mike was talking. So it's probably about that dam. Any archaeological concerns prior to decommissioning and removal of the dam?
Yeah, there was, full historical and archaeological, from both sides of the border, but in particular on the Canadian side, that given the historical pre-settlement use of that area, and there were some locations of interest and careful monitoring of all ground disturbing work at the site. Site itself had been turned over a lot, but nevertheless, a very careful observation throughout the project.
Okay, great. For the Milltown Dam removal, how was water management performed? Were you allowed to work in the wet and use heavy equipment in the river?
Yeah, we could talk a lot about that, but generally, the work in Canada, there was a large cofferdam built out and around the powerhouses, and a tailwater cofferdam to enable the removal of all of the hazardous building materials and the powerhouses and everything on down through their foundations, and at the same time do the bed enhancement downstream of the powerhouses. And then it was flipped over to the other side of the river, coming in with an access ramp from the United States to get those spillways out. And at the very last, 3% of the project there, we were operating in the river to do some fine tuning of things and yank out some last timber structures and stuff. Happy to talk more about that though.
This one's for the Woodland site. Was the fish passage structure considered for the Canadian side? Are there any plans for removal or fish passage for the Vanceboro and Forest City dams?
Yeah. So for the Woodland site, we did a feasibility study with the IJC back in 2019, 2020. We did consider concepts and options on the Canadian side, but we found it was more advantageous to have the fishways near the discharge of the hydropower units. And I'm not aware of any plans for those projects upstream.
All right, and we have maybe 1 more minute here, so there is a couple more questions scooted in. Any upstream passage work for the Grand Falls bypass reach?
Grand Falls upstream passage on the bypass reach, so that's the reach leading up to the actual dam itself. Currently, we had the nature-like fishway kind of sited over on that side. There's a pretty tight pretty steep hillside, geotechnically unstable. There's actually a fault line over there. So we switched that alignment to be on the south side, and leading up into the Powerhouse Canal.
And
Go ahead, Greg.
I'll just add, there's a significant drop in the bypass reach, and that's why we didn't propose fishways up at the spillway. So there's a barrier in the bypass reach.
All right. We are at our time limit. This has been great. I see people have learned to use the the fun icons on there, so you've had a lot of floating applause. So great work. This is just really cool stuff. Do you all have contact information slide at all? Nope. Don't know that you did. There we go. All right. If folks have additional questions, can they email you? Can they ask you about stuff? I think there's maybe 1 or 2 questions on here we didn't get to. Yep, that looks like
Sure,
we've got
absolutely.
okay from everybody there. So copy those emails down, send your questions, and as always, great job. And we look forward to seeing everybody in a couple more months when we do our next webinar. Thanks, everyone. Take care.
Thank you.
Thanks all.
Hey, thank you.
Thanks, Kathy.
Bye.